In this particular video, I'll show you how to write this Lewis dot structures. It's very easy if you follow the simple few techniques here. So I'm going to show you those techniques to how to write these Lewis dot structures here. This is very simple in writing them. So few rules have to be followed. The first one is the first one is the count, the number of its. We know that this Lewis structure is based totally on the valence electrons or the outermost electrons which are present in the each atoms of the molecule. So, the valence electrons are nothing but the electrons which are present in the outermost shell. So, the first calculate the total number of the valence electrons in the particular molecule, and the second one to be kept in mind is it should be follow the all atoms in that molecule should follow the octet rule. The what is this octet rule says that atoms should have 8 electrons in its outermost shell. So that means to attain the nearest noble gas configuration, that is of helium or argon or the second one is neon, then comes argon, krypton. So, in order to attain this nearest noble gas configuration, because the noble gases are very stable, so it want to attain this nearest noble gas configuration. So it should have the 8 electrons in the outermost shell, except for that of the hydrogen, where it will have 2 electrons. It's an exception. It's a doublet of electrons. So they should follow the octet rule, and this is for the and the central atom here may or may not follow the octet rule. So may or may not follow the octet rule. So it need not follow the octet rule here, the central atom, but the terminal atoms should follow this octet rule. So terminal atoms. So these are the conditions. And the fourth one is, how do you select the central atom? The central atom is generally or usually the least electronegative. Central atom is the least electronegative atom is selected as the central atom, or it is having the highest atomic number. Also it's selected as the uh, central atom, and or generally the largest size. So all these, any of these characters of that will be selected as a central atom. Now, and next one is, yeah, next one is the central atom will try to remain in its central atom now tries to remain in maximum covalency. Yes. So what is this covalency? Is the covalency is nothing but the number of electrons the atom can give for the covalent bond. So number of electrons it can give for sharing or the formation of the covalent bond is nothing but the covalency. For oxygen, the covalency is 2. That means it can give 2 electrons for sharing or for the formation of the covalent bond. And for sulfur, it is 6, the maximum, but it can give 2, 4, or 6. Maximum is 6. So generally, the maximum covalency is nothing but the number of electrons in the valence shells. The valency is nothing but the covalency. That's the maximum. So maximum it can give for bonding is its a maximum covalency. And for nitrogen, so it is 3, or sometimes it can form 4 bonds also. And for chlorine, it is maximum is 7, but it can form 1, 3, 5, or 7. And for carbon, it is 4. Yes, silicon also 4 here. Yes. 4, and phosphorus it is 5. So if there is, and next one is, if there is a positive charge, then this charge is usually on the central atom. Yes. And for example is H3O plus. This one is oxygen is a central atom. This is a positive charge is on the oxygen. And if there is a negative charge, this negative charge is on the terminal atoms. Yes, for example, if we, so all these conditions are to be kept in mind while writing the uh, so nitrogen is the central atom here, oxygen is the terminal, so the negative charge is usually beared by this oxygen atom. So all these points are to be kept in mind before writing the Lewis dot structures. First is calculate the number of the valence electrons. Second one is the terminal atom should perfectly follow the octet rule. That means it should have 8 electrons in the outermost shell. And the third one is the central atom may or may not follow the octet rule. And by selecting the central atom in the given molecule, it should be either least electronegative or the largest size or the highest atomic number atom is generally selected as a central atom. And the central atom always tries to remain its maximum covalency, because if when it is in maximum covalency, it is generally very stable. And if there is a positive charge, then this is beared by the central atom, and if there is a negative charge, this is generally beared by the terminal atoms. So these are the points which are to be kept in mind while writing the Lewis dot structures. Yes. So uh, so the first thing we should calculate is the number of the valence electrons. So how these valence electrons are, total number of valence electrons is, so yes, wait just a second. Yeah. So the valence electrons is, so is nothing but the total electrons is total number of valence electrons on all atoms. So valence electrons on all atoms. And then how to calculate the bonding pair of electrons is this 2 into the number of bonds. So and the third one is how to calculate the lone pair of electrons is, so valence electrons minus the bond pair of electrons will give you the lone pair of electrons. So if, and first thing, you take an example of this hydrogen, simple example. So we know that the number of valence electrons or only single electron is present. So 2 into 1 is equal to 2 valence electrons. And first, so there, since there is only 2 atoms in a molecule, write these two with one bond pair, I mean one bond in between, the sigma bond in between these two hydrogens. So and how to calculate this bond pairs is only single electron in this. So bond pairs is one bond into two electrons is equal to uh, two electrons, and this lone pairs is valence electrons 2 minus 2 is equal to 0. So the simple structure that can be written here is this one. So this is a Lewis dot, I mean, structure of this hydrogen molecule. And let's take the example of oxygen here. So simply by, so oxygen, the we know its atomic number is 8. So electronic configuration will be 1 is 2, 2 s 2, and 2p4. So it's 2 and 6, though valence electronic configuration is 6 here. So so as there are two oxygen atoms, so 2 into 6, the total number of valence electrons is 12 electrons here. So valence electrons are 12 electrons. So try writing the structure here. Two oxygens here, put one bond here, sigma bond. So bonding pair of electrons here will be only one bond, that is into two electrons is equal to two electrons. So the lone pair of electrons will be so calculate the lone pair of electrons, the valence electrons minus the bonding pair of electrons is the 10 electrons. How do they put these 10 electrons now? So first write these lone pair of electrons on the terminal atoms. So this is, so 6 and 7, 8, 9 and 10. So I'll write this also in terms of electrons here. Okay. So so then we'll see whether the octet rule is satisfied or not. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So total of 12 electrons. Okay. But for this it is 8 electrons. Okay. But for this it's only 6 electrons. So this octet rule is not satisfied for this. So the structure is wrong. So what do you do? So this 10 electrons, this lone pair can either be used as lone pairs or can be used for multiple bonds, a double or triple bond. So try now will you try, we'll try using this in a double bond here. So what you do is oxygen, so this is the correct structure of oxygen, that is a diatomic molecule with a double bond in between these two oxygen atoms. So we'll see whether this octet rule is satisfied or not. So 1, 2, 3, 4, 5, 6, 7, 8 for this. 1, 2, 3, 4, 5, 6, 7, 8 for this also. So now we'll try writing this for the charged ion. For example, we take this hydronium ion here. So H3O plus. Yes. So total number of valence electrons in this will be, so this is 1. So 3 into 1 plus oxygen is 6 here. So 9, and there is one positive charge in this. If there is a positive charge, so if there is a positive charge on this, so subtract one electron because there is a positive charge. It's a total number of 8 electrons in this. So now the bonding pair of electrons, how to calculate this? First write this oxygen as a central atom. We know that it's a least in number, and there are three hydrogens. Put hydrogens here. So write one sigma bond in between all these. So how many bonding pair of electrons are there? So total number of bonds are 3. There are 3 into 2, which is nothing but 6 electrons here. So how many lone pairs of there? So valence electrons minus bonding pair of electrons, which is nothing but 8 minus 6 is equal to 2 electrons. This now, where do you put this 2 electrons? So hydrogen, we know that it is having so it is satisfying the doublet rule because it's a hydrogen. So 1 2, this hydrogen is also following satisfying the doublet rule, and this hydrogen also. So after after putting the electrons, this lone pair of electrons which are remaining on the terminal atoms, that means that if they are satisfying the octet rule or the doublet rule, then put the remaining on the central atom. Now those are 2 electrons which are remaining on the central atom. So is this done? No, there's still the positive charge which is left. So if there is a positive charge in the molecule, the central atom, we can put this positive charge. Yes. So this is the structure of this hydronium ion with a positive charge on the central oxygen. So 1, 2, 3, 4, 5, 6, 7, 8. So it is satisfying the octet rule also with a positive charge on the central atom. Yes, this is the structure of the hydronium ion. And let's look at the structure of this uh, ammonium ion, that is of NH4 plus. So how, first calculate the number of these valence electrons is equal to nitrogen is 5 into 1 plus 4 electrons, that is 9 with a positive charge again. So minus 1, that is equal to 8 electrons. This nitrogen, it is atomic number is 5, 7. So it is 1s2, 2s2, 2p3. So outermost electronic configuration is 5 here. So 5, and hydrogen is 1 with a positive charge, so minus 1. That's the total number of electrons are 8. Now nitrogen is a central atom. It's with hydrogens on the 4 sides. We can put them, and now put these single bonds here and between all of them. And now the bond pair of electrons are, there are 4 bonds into 2 electrons, 1, 2, 3, and 4. So 8 electrons. So the lone pair of electrons here are 0 because valence electrons minus bonding pair of electrons is 0. So there's a positive charge. So write this on the central atom here. So yeah, this is the structure of this ammonium ion, and I'll discuss few more structures in my next video.